The death of the power-hungry GPU. A single silicon chip the size of a postage stamp just ran the entire Llama 4100 billion parameter model using less power than a standard LED light bulb. This is not a software trick or a clever compression algorithm. We are seeing the first production-ready ternary native processors that replace complex floating-point math with simple addition. This shift effectively kills the thermal wall that has protected the GPU monopoly for a decade. The energy math that governed the last 5 years of AI development has been completely rewritten by the end of multi-accumulate logic, eliminating the multiplier bottleneck. Standard GPUs waste 90% of their energy on high-precision multiplication because traditional AI weights are 16-bit numbers. But the bitnet architecture proved that models only need 3 values: -1, 0, and +1. By moving this logic into dedicated 1-bit NPUs, we have eliminated the need for massive floating-point units. These new chips replace energy-hungry multipliers with simple accumulators that just add or subtract. The result is a 70-fold increase in energy efficiency compared to the H100 architecture we relied on in the early 20s. This hardware optimization is the exact reason 100 billion parameter models no longer require a server rack. The physical footprint of intelligence is shrinking because the math is getting simpler, not more complex. This reduction in complexity is what finally unlocks the ternary advantage. The ternary advantage. If you think 1 bit means losing intelligence, the data from last month's ML-Perf benchmarks proves the opposite. Ternary logic actually acts as a regularizer, forcing the model to learn more robust features rather than memorizing noise and high-precision decimals. A 1-bit model at 100 billion parameters now matches the reasoning capabilities of a 16-bit model of the same size, but it fits into 12 gigabytes of memory instead of 200. The devil's advocate view is that training these models still requires standard high-precision hardware, but the inference side is where the monopoly breaks. Once a model is baked into ternary weights, it can run on almost anything. This massive reduction in memory bandwidth requirements is the secret to the 10-watt barrier. Breaking the 10-watt barrier. Reaching the 10-watt threshold is the holy grail for edge computing because it means high-end reasoning can happen inside a pair of glasses or a drone without a cooling fan. The recent release of the Oxide 1 NPU demonstrates that we can now process 30 tokens per second on a 100 billion parameter model while drawing only 9.2 watts. This isn't just about saving electricity at the data center. It is about localizing intelligence so it never has to touch the cloud. When the hardware cost drops from $30,000 per GPU to $200 per NPU, the centralized cloud model begins to look like an expensive relic. This fundamental shift in price-to-performance ratio reveals the decentralized compute payoff. The decentralized compute payoff. The shift to ternary native silicon marks the definitive end of the era where AI capability was strictly tied to capital expenditure. By merging the efficiency of 1-bit weights with the 10-watt power profile of the new Oxide 1 NPUs, we are transitioning from a world of massive data centers to a world of ambient intelligence. This means the moat for big tech companies is no longer their massive GPU clusters, but their ability to integrate these specialized chips into consumer hardware. For engineers and strategists, the priority has shifted from cloud scaling to local integration. The bottleneck is no longer raw compute power, but how effectively we can deploy 100 billion parameter reasoning at the edge. Watch the upcoming June 2026 hardware integration cycle for the first smartphone brands to announce built-in local assistants that operate entirely offline. The era of the GPU monopoly is officially over. Subscribe for more.